The second corollary tells you that if a line is parallel to one side of a triangle and intersects the other two sides, then the triangle formed is similar to the original. In words, you might need to think through that, but in reality, if you see just a triangle, let's pick this side as the side we want to create a parallel line for. So let's say this side here, this line is parallel to that line. Then this triangle that's formed is similar. I think we understand that, but great corollary. You have that as a tool now in your tool kit that you can use, that you will be using as you do these proofs. So that's 15 through 18. So we covered 15 through 18 on page 19 and following. Look at all of the fun things you get to do on page 19. It starts off with 3 different triangles that are drawn across the top of that page, 5, 6, and 7. Similar to what we've got here. They're all similar to that, just formed differently, but does that matter? Not really for doing these proportions. So number 5, we'll start with that one. So this is page 19 now. So now we're on the second part, page 19, and number 5. DB blank, EC blank, and you've got a triangle. That's labeled A, D, E, and B, and C. Some of the sides are given to you. There's a 9, an 8, a 6, and a 10. The first thing I want you to find is DB. Where's DB? DB is right here. So right here is DB, that little section with the red mark next to it. You need to be able to find that given what you have. What would you do? What would you do? You would set up a proportion, of course, because that's what we're learning in this pace. Ratios, fractions, proportions. What proportion would you choose? If we're starting with this nice big triangle here, ABC, this is a separate triangle that could potentially exist separately as ADE with 9, 6, and 8 for its sides. And then I have a larger triangle and I only know 10. I don't know these sides because that's actually what we're ultimately going to be finding. So we separate out the two just so you kind of get an idea of what I know, what I don't know. It's a little clearer to see that this is ABC and this one is ADE, which I know all the sides of. This one I know is similar to it, but I don't know the sides. How could I find them? Well, I couldn't unless I know that this triangle is inside this one. Then I can set up a proportion. So if I go with my larger triangle 10 over my smaller one 6 and set that equal to this side, the larger side AB, and that is over what? What would that be over? You tell me. 9? Where'd you get 9? Yeah. So side 6 is a part of that triangle right here, and so is 9. So those correspond, and 10 and the unknown correspond. Does that make sense how you set up that proportion and why? Mm-hmm. Now you could set it up with all of these being labeled as the sides or sections. Hopefully you can follow that. Now, we got to solve it. Are you able to do that? I would just leave the AB in there, 6 times AB, just so we remember. But AB, you could substitute some other letter for that, X, Y, something else. As long as you know what you're finding. Now I have 6x, or unknown, equals 90. So I need to divide both sides by 6 to get rid of the 6. And side AB is 6 goes into 90 how many times? 15. Am I done? Is that my answer? Is that what goes in the blank?
Sure.
No, it's AB.
Oh.
We're supposed to find BD or DB.
Subtracted by 9.
So I'm supposed to find DB. Now this is where the danger of, danger, if you want to call it that, if you just put X here, you might have solved for X and thought, hey, I'm done, and write that in the blank, but it's actually not your answer. The answer is 15 minus 9, because BA is what we found. So I need BA minus DA is going to give me DB. See that? Those two add up to that whole thing. And 15 minus 9, of course, is 6. So that's what goes in your blank. So you do the exact same thing to find EC, and in fact, the exact same thing to find all of these missing sides all the way across. Now, if you peek over at number 7, you'll see they made it just a little bit extra. So side AE isn't a number. Side AE is an x plus 1. And side AC is not a number, it's 4x minus 1. So you get to use those to solve, but you can in fact solve for those and get a number answer. It will not involve an x. You can solve for x there using the same proportion. So just set a proportion, solve for x, and you will get it, I am sure. Let's take a look and make sure we can recognize what theorems or postulates to see if these give you any trouble. If they give you trouble recognizing which one it is, then that's a clue that you need to study them just a little bit more to get ready for the test. Do you suppose you need to know all of these on the test? Yes. Be prepared. So 8, 9, 10, 11, and 12 are all great things that you want to study and review. Let's see if we can't recognize them though. Given that drawing, the triangles there, number 8 says angle A congruent to angle A, and B congruent to ADE. Which theorem or postulate does that sound like? In other words, we just proved those two triangles similar because those two angles are congruent. What theorem does that sound like to you? The angle similarity theorem. That's theorem 87. Now this next one, angle A congruent to angle A, B congruent to angle ADE, C congruent to angle AED, and all those sides are proportional. What meets all of that criteria? It's the definition of similar polygons. These are polygons that have their corresponding angles and lengths of corresponding sides are proportional. Number 10. Triangle ADE and ABC are right triangles. Oh, and angle A is congruent to angle A. Which theorem? I would suggest that we use the right triangle similarity corollary. That's the first corollary of theorem 87. Remember, there was a second one as well. Number 11. All three angles are congruent. Which theorem or postulate tells us that all three angles are congruent, then the triangles are similar? It's the aptly named angle similarity postulate. Postulate 29. if you turn the page all the way over one page, on page 18, Theorem 87, Corollary 2 says, if a line is parallel to one side of a triangle and intersects the other two sides, then the triangle formed is similar to the original triangle. Does that describe what you see in the picture? It does. Because DE parallel to BC. So that is the one there. So some of those a little newer, some of those a little older. Make sure that all makes sense to you. Definitely need to know those, how to recognize those, how to use them in proofs. All right, speaking of proofs, now we've got a whole run of them. Look at page 20, 21, 22, 23. All these proofs, proof. So proof number 1, let's jump right in on page 20. Can anyone tell me what's in that picture there? There's a picture on this page. What is in that picture? A square. It looks like a triangle to me. It is. It's a square. Again, if you're working with triangles like that, you're trying to prove them similar and they're drawn on top of one another, it's probably best to draw them separately and orient them so that way they look like they're matching. The advantage you have here is there's a right angle because it's a square, which is a triangle, but it's a square, which has a right angle to it. That's one of the things you use a square for, to determine when you have right angles. If you're just watching this and not understanding what we're talking about, calling a square a triangle, it would be very confusing, and vice versa. So just look at the picture. The picture is a triangle, but it's actually a square, is what the thing is called that's a picture of, but it's actually in the shape of a triangle. Proof number 1. Draw your shapes separately. Those are your right angles. A, B, and C. And this one is C, Z, and X. Now this one is C because it's that same C, correct?
C.
I mean, it essentially does matter because this triangle, if I flipped it that way, it stuck it right there. That's what's going on. If it was the other way that I tried to draw it, the triangle would sit like this with a right angle there. But that's not what's happening. The line actually goes through here, but we don't need to see that right now because we have it drawn over there. All right, off to a running start, I can see. But we're getting there. Sometimes it's messy. Proof number 1. You've been given all of that. This triangle, that triangle, right angles, B and X, Z, C, respectively. They even give you step 2. Triangle ABC, triangle XZC are right triangles. And of course, when you have just made the statement, the claim that these are right triangles, what is your reason for that? Basically every time. Definition of right triangles, of course. Angle C congruent to angle C is what you should put next because we recognize we've got the same angle. If you're dealing with overlapping triangles, generally it's being drawn that way to show that they're sharing an angle, which means you're always going to be looking for the what property? Reflexive.
Oh, that one.
That's reflexive. C is C. That's reflexive. This happens to be an angle and not a line, but it works both ways. They give you 4 and 5. What's your reason for 4? To be able to claim that the triangles are similar. We just proved that they are right triangles. We just labeled the right angle. And then we just proved another angle congruent. So, what theorem should we use? The right triangle similarity corollary. And if you'd like to see, and I would highly recommend you look carefully at this proof, it is on your study guide as a reference. When we learned the definition of similar polygons, as you can see written here in the reasons, way back in the PACE, here, I think, is the first appearance of it showing up in a proof, I think. I definitely made note of it as an example. When you're studying for the test and you want to know, how will I apply definition of similar polygons for the fun little exercise we get to do in the future? So that is where you see it used, you see it written, read that, make sure you understand why definition of similar polygons applies there. There's a second proof at the bottom of the page where you've been given TU parallel to RS. Now that sounds a lot like which theorem? Theorem 87 Corollary 2? The one that you've got two parallels? Yeah, it does. Well, they gave that to you. That's in your given. So does that mean then, based upon the drawing, the very next thing you'd be able to say, truly, is that those two triangles are similar? You gave me that this line parallel to that line. Are the triangles similar? Am I ready to say that? Just right away? Can I say triangle QTU is similar to triangle QRS? And you would say, yes, you can say that. And the reason, Theorem 87 Corollary 2. Now you know your proof statement is TU over RS equals QT over QR. But what would you put as your reason? Look at the first proof, hint, hint. You got it? You know what you put for your reason? Yes? I hope so. I'll leave that right there. Next page is on 21. This looks like a somewhat lopsided, but albeit geometry bow tie. Lopsided or not, they're great. Sadly, what you would assume would make an appearance doesn't make an appearance. No. Vertical angles congruent? Not part of it. Something else makes an appearance though. Let's see if you catch it. You have your given, there you have perpendiculars. See that as your given? Proof statement number 2 is blank, and so's the reason. So's 3. So's 4. Well, we see where we're trying to get to. There's another example of definition of similar polygons. How do we get from this is perpendicular to that all the way down to similar polygons? How would we get there? Well, what do you need to know in order to prove similar polygons? So refer back to your definition of similar polygons. Those are polygons that have their corresponding angles congruent and the lengths of their corresponding sides proportional. So that means we're going to need to prove corresponding angles congruent, sides proportional, those pieces. Any guesses on how to get started? Well, what do you know about perpendicular lines? If AB is truly perpendicular to BS, and so is RS, also perpendicular to the same line, what do you know about those two lines? So break it down in this way. I've got a line. Lines just living here. SB matches what's in the PACE. And I've got this line here and this line here. These are perpendicular. So these two, with respect to each other, would be parallel lines. Do I have a theorem that involves the word parallel? Look back, find one. Is there something that says this is parallel? You have something that maybe says if two lines in a plane are perpendicular to a third line, then they are parallel to each other. That feels like a way back theorem. You remember that one? So if two lines in a plane are perpendicular to a third line, then they are parallel to each other. So here's our two lines perpendicular to a third line. That makes them parallel. So you would claim then that AB is parallel to RS, right? Well, that's useful because now I have RS here and AB here. And I've got this line that connects the two like that.
That was actually a decent line.
I already know that these then are right angles. Do I have anything else? Parallel, right angles. I need to be able to find angles that are congruent. This angle and that angle. And I know this is parallel to that. Perhaps if we got some of the distractions out of the way and we drew our old friend this, remember when we were drawing this, what was the term we were using all the time? Transversals. Oh, remember transversals? And we know that if a transversal intersects two parallel lines, then the alternate interior angles are congruent. Would this be alternate interior angles? So I'd be able to say that is congruent to that. Yes? Then that would work. Now I can prove that my triangles are in fact similar. And once I have my triangles are similar, then I can say that AB over RS is equal to AT. Where's T? It must be in the middle. AT over RT. Got it? That's proof 3. So we're actually doing proof 3 on not page 19, but page 21 there. So that's proof 3, page 21. Now, these angles are also congruent, right? Why do we just use that? Could you have?
Probably.
Probably. Okay, I like the positivity. So you can work on that as extra credit. You wonder why we don't get anything done. Page 22. Anything on page 22 that we need to address? Let's see. Oh yeah, these are actually both important. 22, proof number 1. This section is telling us about the product of the lengths of two segments. So if you read that little introductory paragraph at the top, page 22, it says the proportionality between corresponding segments of two triangles can be established if similarity exists between the two triangles. By applying Theorem 84 in a proportion, the product of the extremes equals the product of the means. Remember that? Theorem 84? The cross multiplication. We can go a step further. Look at what we get to prove. You've been given DE parallel to AB. So rather than drawing it this way, it's drawn the other way.
Like the Adidas symbol.
Like that. EC times AC equals BC times DC. Look at all of that. That's a lot. How would we even begin? Well, they didn't leave you much room for thinking on proof number 1, did they?
Good.
But what is the one missing piece that you do get to think about and fill out? Well, look at the reason. If a line is parallel to one side of a triangle and intersects the other two sides, then the triangle formed is similar to the original. So would we say that those two triangles are similar? I mean, that's what the reason is telling us we can say. Definition of similar polygon shows up, and you see how they have set the sides in a proportion. Or how would you get from 3 to 4? That's just the cross multiplication step. Product of the means equals the product of the extremes, or vice versa. So I wanted you to look at that proof so we could take a close look at the note, because you want to make sure that the note makes sense to you. Look at page 22, right in the middle, note. To show equality of the product of the lengths of one pair of segments to the product of the lengths of another pair of segments, these 3 things. Number 1, establish similarity between given triangles. Did we do that? We did. That was step 2. Number 2 under the note, set up a correct proportion with the lengths of the sides. Was that done? They did that for you. And then finally, apply Theorem 84 to get the desired product. They did that for you. So you see how 1, 2, and 3 correspond to steps 2, 3, and 4 above? You think you would need to know that and maybe be able to do something like that in the future? Yeah. I would want to be able to do this kind of thing. Recognize it, see it, work with it, write it out. Look at proof number 2. On the bottom of page 22. We have a different kind of shape. Whoa, what's happened? We've got a triangle, like always, but the other one is like this.
Okay.
A, B, and C are there, just like always, but D and E, it looks like one of these sides isn't holding up the end of the bargain. It's like crooked. What would we do there? Well, they labeled this as a 2 and a 1. Let's pay attention to that. Oh, hey, that's in my given. Angle 1 is congruent to angle 2. Oh, now I'm starting to see how this comes together. Do you think this might be another example of when to separate them and draw them separately? So if 1 is 2, then I could do that. That would be 2, right? That's E. That would make this D. And that A or no?
Yes.
So here I'm taking it, and I'm not just moving it over here, I'm actually flipping it around. Right? Mm-hmm. Yeah, okay. Now the way I drew it doesn't quite match the triangle too well. Maybe it should do that. Ish. It's iffy. It's close. You'll do a better job, I'm sure. But we had one triangle sitting on top of another, so that angle A is the same in both. So you want to go right for that. Statement number 2. Angle A congruent to angle A. And of course our reason for that is angle A is A. Reason is reflexive. We've got step 3, step 4 to figure out, and 5 is our here's what I'm proving. Well, what do I know? I have an angle that's similar. Oh, and another angle that's similar. That makes me think that I might have what? I've proven 2 angles are congruent. If I have 2 angles congruent in triangles, then I could say that they are similar. Why? So triangle ABC, similar. Ooh, That's just getting worse. To triangle let's see, I have A, B, C. I want to do A, E, D. Why?
Corollary 2.
My angle, similarity theorem. Yes? Okay, good. Next, we have definition of similar polygons. It seems like every time we have definition of similar polygons, that the statement we have given and use this is a proportion. So what proportion would you write in step 4 or statement 4? Well, I would see that I have BC and ED, and that is equal to what? AB over AE? Yes? Yeah, I can make that statement. Why would that be convenient for me to make that statement? Well, look at what I'm trying to prove is that BC times AE is equal to ED times AB, the cross multiplication. And when I do that, what theorem do I use? Of course, it's the Theorem 84. That gets us through page 22. You also have page 23 to do, as you can see, which is even more proofs to finish up.
One. You took that away.
And one of the proofs on page 23 is extremely useful for your future.
There's only 2 and you're making us skip them.
I did? Which one did I make you skip?
The important one.
Why would I do that? So in your homework, it says you can skip proof number 3.
Sinner.
That'll be like a little Easter egg for those who watch this later, I guess. All right, so pay attention. Proof number 4.
Later.
Huh?
It's not like Isaac's gonna like, oh, I get to skip number 3 because Mr. Chris said.
He might. I don't know.
Mom, Mr. Chris said skip it.
He said skip 3. Do 4. Pay attention to 4. Really know 4. Yeah, so if you're hearing anything, you're hearing really know 4. Like really, really, really know 4. So do that well. Come back to class and show it to me next time we meet. Got it?
Okay.
All right.
Bye.
Goodbye.